Good morning, everyone. I welcome all the participants, guest speaker, faculty coordinators for the AICT ATL-sponsored online faculty development program on quantum computation and information science held between 4th to 8th Jan 2021, organized by the Department of Electrical, Electronics and Communication Engineering, ETHM, deemed to be University Bengaluru campus. In this morning, I welcome you all for the first session on quantum bit and quantum gates, handled by Dr. Harish Sahu, scientist in Defense R&D Organization, Delhi. I now take the privilege to introduce the speaker of today's session, Dr. Harish Sahu, scientist E at Scientific Analysis Group, SAG, DRDO. Dr. Harish Sahu did his BE from Government Engineering College, Ajmer in the year 2004. After completed engineering, he briefly worked in L&T Infotech and Yardley Infotech MNCs as software engineer in Bangalore. He then joined DRDO as Scientist B in April 2005 and worked on modeling and simulation of infantry weapons for war gaming projects and information security project at ISSA during 2005 to 2012. And in the year 2011, Dr. Harish Sahu completed MTech in cryptography from IIT Delhi. Dr. Harish Sahu worked on crypt analysis of practically used stream ciphers at SAG during 2012 to 2017. He has been awarded PhD in cryptanalysis of symmetric ciphers using ROBS and SMT solvers in 2018 from IIT Delhi. At present, Dr. Harish Sahu is working as Scientist E at SAG. His current research interests are quantum computing, quantum cryptanalysis, and quantum cryptography. I welcome you, sir, for today's session, and I hereby hand over the session to Dr. Harish Sahu, Scientist E at Scientific Analysis Group, DRDO, Delhi. Welcome you, sir.
Good morning, all. Kindly wait for 2 minutes. Sir is facing some technical issues, so he will join soon. Yes, sir joined.
Yeah, hello, good morning. Hello. Hello. Hello.
Yes, sir, you are audible.
Okay. Good morning, everyone. Myself Harish, and there was some issue at my side. So, yeah. So, are you able to see my screen?
No, sir.
You're not able to see my screen, my laptop's screen?
Yeah, it's Zoom.
Yeah.
Yes, sir. Yes, sir. We can see, sir.
Okay, just a second.
Visible, sir.
Yeah. Yeah, thank you, Dr. Panda, for nice introduction, and thank you for the GITAM team for organizing this FDP and inviting me to deliver talks. So today we will going to cover in the first session about quantum bits and quantum gates and how they are used for computation and quantum computer. So the agenda of my talk today is firstly we will just briefly uh, cover this classical logic gates so that we can understand the quantum gates and the qubits better, and then we will be covering quantum bits, and then we will be covering quantum gates. In that we will be covering both single qubit gates and multi-qubit gates. So let's start with classical logic gates first. So everybody is aware about this classical logic gates, which are used for whatever computation we do in classical computers. It boils down to this classical logic gates, and using those gates, the computation is performed. So firstly, this very basic gates, NOT and OR gate, we will cover. So, Sunita ma'am, if something like audio video problem happens, then interrupt me in between. Sunita ma'am? Hello?
Yes, sir. Sure, sir.
Yeah, so I'm audible and slides are visible. If
Yes,
any
yes,
issue
sir.
arises.
Yes, sir.
Okay, thank you.
Thank you, sir.
Yeah. So firstly is this NOT gate. So what is a NOT gate? Basically, it's take a single bit input and it complement it. If the input is 0, then it will change it to 1, and if input is 1, then it will change it to 0. So this gate is kind of reversible. If we know this Y, then we can tell about what was the input X. So if we apply this gate 2 times, then we will get original X. So here we are applying 2 NOT gate in sequence. So we will get the original input X at the after application of these 2 NOT gates. Next come is AND gate. What does an AND gate does? It takes 2 inputs and produces an output Z, such that whenever both the input X and Y are high, then only Z will be high. So basically when X and Y are 1, then only Z will be 1. For other rest of the inputs, it will be always output 0. So here we can see this AND gate is like not reversible. Like previously, if we apply NOT gate 2 times, then we will get the original input X. But here in case of AND gate, what will happen? If we are given some Z is equal to 0, then we cannot tell about the input with surety that whether it was 0, 0 or 0, 1 or 1, 0. So if given output Z 0, we cannot tell about X and Y surely. So basically this gate is kind of not reversible. Given the output, we cannot tell about what is the inputs. So this phenomena of reversibility is useful in quantum gates that we will discuss. Next is another important gate, that is OR gate. So what it does is whenever one of the input X or Y is high, then the output will be high. So here we can see In case of 0, 1 input, it is high. In case of 1, 0, in case of 1, 1, so it is high. Only when both the input are 0, then only it will be output 0. So next comes is NAND and NOR gates. Basically, those are consist of these basic gates only, but they are used as universal gates in our classical computers. So this is the NAND gate. So as the name specify, it is basically doing first doing the AND, then applying NOT over it. So basically, first we do some ANDing, then we will apply NOT gate. So here we can see the truth table also. So firstly, this is W is basically the AND gate table, and then we were complementing it. So this is the thing we will get. So what is this NAND gate is basically does is it's first AND the inputs, then complement that. So whenever both the inputs are 1, it will produce 0. In the rest of the cases, it will always produce 1. So here also we can see that first ANDing, and then we apply NOT over it. So this is the symbolic notation of NAND gate, and this is how we write in some assembly programmings. Similar to NAND gate, there is also a universal gate called NOR gate. So what it does is just does the ORing of 2 inputs, then apply NOT over it. So here we can see the truth table. First W is the OR output, and then we are applying NOT over W. So we are getting Z. So basically, whenever both the inputs are 0, then only we are getting 1. Otherwise, it is 0. So here just you can see here. So basically, first we are producing this W and applying NOT over it. And what is W? W is basically X or Y. So this is the symbolic notation for NOR gate. And so what's a universal gate? Can anyone tell? Dr. Panda, allow some participant to speak, or you can unmute all. Dr. Panda? Or any of the organizers?
Sir, yes, sir.
I am requesting you to unmute all the participants, and one of them let's answer.
Yes,
the
sir.
question.
Yes, sir. Yes, sir. Sure, sir.
So my question is, what is a universal gate in case of classical computing or classical gates? Here we are saying that NAND is a universal gate. So at a time, one participant try to unmute himself or herself. Yeah, please.
Basically, universal gate is that using only that we can simulate all the other gates.
Yes. So let's suppose I am saying this NAND is a universal gate. So can you construct a NOT gate using it?
Yes.
Can we?
Yes, sir.
Yes, sir.
So for that, what we should do? Let's suppose we are given this NAND gate, and I want to use this NAND as a NOT gate only.
Both the inputs should be shorted, sir.
Shorted.
Then
Okay.
output will be complement of the input.
Okay, that's good. And let's suppose I want to use it as an OR gate, or let's suppose I want to use just for a AND gate.
And
Can I use it as an AND gate?
yes, sir.
Yes.
It can be connected at the output.
Yes, sir.
How?
And single.
The output of the NAND gate should be connected to the NOT gate. NOT gate again can be implemented using NAND gate, sir.
Yeah, perfect. So basically, you are saying that we will use 2 NAND gate, and then it will be done.
Yes, sir.
Yeah, correct. So basically, using this NAND gate, we can construct all other gates. Okay. So this one NAND gate is sufficient to derive all classical logics or the Boolean logics. Similarly, using OR and NOT also we can do all the things. Kindly mute yourself once you speak, participants. Mute yourself once you have spoken. So here I am saying that OR and NOT is also a set of universal gate. So using this OR and NOT, we can construct NOR gate, and using NOR, we can construct all other gates. So basically, the idea is that universal gates can be used to produce all kind of Boolean logics or all kind of derived gates we can construct using these gates only. And next is De Morgan's theorem. So what it does is, using this theorem, we can construct, we can change from AND to or to AND, so that we can implement our logic efficiently. So here, what is the De Morgan theorem tells that if we are having this kind of NOT gate, then we can construct this NAND as OR also. So what we are doing here is just we are, let's suppose here X and Y are the input and Z is the output of this NAND gate. And if we do like this, we complement X and Y, basically applying NOT gate and then ORing. So we will also get the same Z. We can see here in the truth table also. So firstly we are doing AND and then applying NOT. And here what we are doing, firstly we are applying NOT and then doing ORing. So if we see the truth table of these two, we will find that these two circuits are equivalent. And that is basically De Morgan's theorem, which tells that the negation of disjunction is the conjunction of the negations. So basically what we are doing is disjunction we are doing here and then applying NOT. Here what we are saying is firstly apply NOT and then do the conjunction. So both the things are equal. So if somewhere we are given this kind of expression, Boolean expression, then we can write it like this also. So basically here we are applying this AND gate, and suppose we are not given AND gate, then we can write in terms of OR also. So basically idea is that we can convert AND to OR and OR to AND using De Morgan's theorem. So next is also like we are given some NOR gate. So NOR gate truth table is given here, and here we are writing it as, firstly we are doing the negation of the inputs and then ending. So basically here if you see, here we are doing ORing and here we are doing ANDing. But these two expressions are equivalent. And here the De Morgan's theorem's other statement that is similar to the first one. Let's say the negation of conjunction is the disjunction of the negations. So these two are equivalent. So what is the rule for De Morgan's theorem that we will see? So if we want to use De Morgan's theorem to convert from one formula to other, then the idea is that first not all the variables, then change AND to OR, and if OR is given, then change it to AND, and finally apply NOT on the result. So here we can see like NOT of X or NOT of Y is given, then we can apply NOT over everything. So it is also NOT, it is also NOT, and the formula is also NOT. And this 2 times NOT is cancelled out. So here we can see that we are getting this expression, that is basically NAND gate. Similarly, other expressions are derived, and what we are finding here is this 3 steps if we apply, then we can convert AND to OR to AND, and it is very useful when we convert the Boolean formulas. So these 3 steps if you remember, then we can do the changes. Next is one of the most important gate, that is exclusive OR gate. So can anyone tell what does this gate do? Any participant, please?
If the inputs are different, output will be high, sir.
Yeah,
If the
correct.
inputs are same, output will be 0.
Correct. So what's your name?
I am Jani Basha.
Jani Basha. Okay, you are correct. And as you told, whenever the inputs are same, basically 0, 0 or 1, 1, then it will produce output 0. Whenever inputs are different, then only it will output high. So here we can see the truth table, and basically OR is there, and this symbol makes it XOR. So denotation of this XOR is like this. And if we write in Boolean formula, then we use this symbol for XOR. Suppose we are given this, we are not having an inbuilt XOR gate. So how we can construct this XOR gate using the basic gates? Suppose we are given this AND or NOT gates, basic gates we are given, and we want to derive XOR. So if we see, the Boolean expression for XOR gate is X Y bar plus X bar Y, or also it is equivalent to X or Y into X Y bar. So basically we are trying to implement this logic. So what is basically we are doing? First 2 input are OR, and again in the 2 inputs are ANDed, then apply NOT gate. So what is this basically? XY bar is,
Sir, आज दिन जाक जाकर का अछि हरीश सरंगर का नहीं
sorry,
ने हम ओडिया ना ओडिया साहू
No,
आ कोन अछि अन्य
no, I am Harish
Avani
Sahu.
Sahu,
I am
sir.
from Rajasthan.
हां
So whenever we are having like suppose we want to implement this logic, so basically what we have to do is we have to just over these inputs and then apply. This is basically NAND gate. What is we are doing here is XY and bar then again. So firstly we are applying this XY using this AND gate, and here we are applying OR gate, and then we are doing NOT. So basically we are having these two expressions here at the input, and then finally we AND them. So after ending this we are getting this. But we see here that to implement this XOR gate, we require 1, 2, 3, 4 gates. So whenever we are doing this kind of derived gate, we should try to keep the number of gates we are using to derive the gate at minimum. So like the same logic can be implemented with other combination also, but every time our goal is to use minimum number of basic gates to have the derived gate. Similarly, this XNOR gate is basically just XOR and then we are applying NOT over it. So that is XNOR gate. And here we can see the truth table. It is just opposite of that XOR gate. So here, whenever the inputs are same, then it is output high. Otherwise, it is 0. So sometimes we are having this kind of situation where we are having multiple inputs. Till now, we have seen single qubit gate and 2 qubit gates. So there is only one single qubit gate, one bit gate, that is NOT gate, and the other gates are 2 input bits gates. Suppose we are having this kind of scenario where we want to implement this kind of AND gate where 4 inputs are there and we want to AND all them. So this kind of multiple input gate scenario occurs while we implement various algorithms. So how to do that thing efficiently? That is our concern. So can anyone tell if suppose I want to implement this logic, how many gates are required? How I will implement this gate? 4 inputs are there and we want to produce output Z1. Can anyone please? Let's suppose it is 1, 2, 3, 4 is the input.
Two input AND gates, sir.
Okay, one AND gate you are applying here.
2 input AND gate.
Yes.
Three such 3 input 2 input AND gates. If we connect, you will get 4 input.
Okay. So yeah, correct. So basically we can do this kind of thing, but always keep the thing in mind that we should do the thing logic implementation using minimum number of gates. So it can be done in other way also, where more number of gates are required. So we will see how we are going to do this. So this is our multiple 4 input gate. So as told by you that first we apply AND here, then we apply AND here, and then we will apply AND of the result of these 2 AND gates. So we will get this kind of logic implemented. So there basically we will require 3 AND gates. If we do without optimizing, then we can use 4 also and then implement the same logic. But always our goal is to use minimum number of gates. Similarly, this multiple input OR gate. So what is happening here is, if one of the input is 1, then it will be output high. So its output will be low only when all the inputs are 0. Similarly, this NAND gate. So basically, whenever all the inputs are high, then only it will be low. Similarly, this NOR gate also. So when will be this Z4 high? When only all the inputs are low, then only it will be high. So till now we have covered classical logic gates, and then the main thing is that similar gates are there in quantum scenario also. So there are, other than this classical logics, other gates are also there which are not having analogous in the classical scenario. So and the universal gate concept is also there. So before moving to that, we will first cover the quantum bit, which is analogous to classical bits, but with certain differences. Just a second. So firstly, we will go through a very basic definition. So what's a quantum computer? It is just similar to the classical one. Instead of it operates on classical bits, it operates on quantum bits and using the quantum gates to perform meaningful computation. And what is the quantum bit? Quantum bit is just analogous to the classical bits. In case of classical, bits can be either in 0 or 1 state, but here it can be in superposition of both 0 and 1. So this we will cover in detail in the coming slides. So how it gives us advantage. And quantum gates are similar to the classical one, basically to perform some meaningful operation on quantum bits. So suppose this psi is our quantum bit state, and we will apply some quantum gate, then the quantum gate will manipulate its state. So it's not like that classically, if we see the bits, then there are only two options. Whether it is, let's suppose some bit B is there, it will be either 0 or 1 at a time. It will be 0 or 1, cannot be both. But, and only two possibilities, that is 0 and 1. But in case of quantum bits, what we are saying is that it can be simultaneously with all possibilities of 0 and 1's linear combination. So basically what we are saying is, let's suppose this psi is a 1 qubit state. So what we are saying here is that can be in linear combination of both 0 and 1. So it can be present both 0 and 1 states simultaneously, that we will see in detail. So what is the idea here is that if we are having 1 qubit, then it can represent 2 choices or 2 amplitudes or 2 bits. If we are having 2 qubits, then it can represent 4 amplitudes. So basically, if we are having n qubits, then it can represent 2 to the power n bits. So let's suppose if we are having in a quantum computer, what happens is, so see here this diagram. In case of normal computer or classical computer, what happens is, let's suppose if we are having some 4-bit input is there. So let's suppose these 4 bits are 1101, and we want to perform some function f on this, and after f we will get this result 1001. So what does happen in the classical computer? It will take this input, one input, basically 1101, and produces the output. Suppose if we want to apply this f for all choices of these 4 bits, then what we have to do is we have to call again this f with different values of those 4 bits. So we will first call for f 4 zeros, then 0001 till 4 times 1. So in this scenario, what is happening here is the normal computer, we are linearly applying this all choices one by one. While what we are saying here in the quantum scenario, if we have 4 qubits, then this 4 qubit can represent all the possible states, starting from all zeros to all ones. So whenever we are having this 4 qubit system, it can represent all possible 4-bit values. That is here 16 values it can represent simultaneously using the 4 qubits only. And when we apply this function f on a quantum computer, it will perform f on all these values simultaneously in one go and produces the output. So here we can see like the 1101 is producing 1001. So we can see here also this 1101 is producing the output here. So this is called quantum parallelism. The first thing that we are telling is it can represent all the inputs simultaneously, 4-bit choices simultaneously. That is called superposition. And on this superposition state of 4 qubit, if we apply some function f using quantum computer, then we will get fx for all possible values of this 4-bit input x. So are you able to appreciate or understand the concept? What is happening in the quantum computer and what happens in normal computer? Can anyone please explain? Or if any doubt, then I will try to explain again. Please, anyone?
Sir,
Yeah, please.
there is actually one doubt.
Yeah.
So we said that like n qubits is going to give rise to 2 to the power n possibilities,
Yes.
all states.
Yes.
But when we are talking about superposition,
Yes.
it is what is alpha naught and alpha 1? It's a linear combination of alpha naught and alpha 1.
Yes.
And alpha naught and alpha 1 belongs to
These
complex
are complex numbers.
Yeah, so then are the number of possibilities not more than 2 to the power n then?
No. Don't think in that way. Choices can be anything.
Yeah.
Let's suppose this alpha 0 and alpha 1 having some value p or q. Then that state is fixed, na? It can take any values, but at a given time, it will take some particular value. At some instant t, it will having some value alpha 0 and alpha 1. So some fixed value will be there. So there can be an infinite number of states, but at a time, some values of alpha 0 and alpha 1 will be fixed. And those will be like this, that mod square plus will be 1. So basically, what is this alpha 0? So alpha 0 is basically the amplitude of 0 state, and alpha 1 is amplitude of 1. And this mod alpha 0 square is basically the probability of getting 0 on measuring this state psi. So this is the superposition state, and when we measure it and convert it to classical one, then getting 0 on measuring this state probability is alpha 0 mod square.
Okay, sir.
So this quantum parallelism, I want one of you to explain whether you understood correctly or not. If anyone understood correctly, then please let us know that how this normal computer operate and how this quantum computer operate.
Sir, what I am trying to understand is actually in normal classical computers also, if n variables are there, 2 power n combinations will come. But here it simultaneously is being applied, sir, all the possibilities. That is the difference in quantum computers.
Yeah.
Because the possibilities, number of combinations are same, 2 power n in both classical and quantum.
Yes.
The difference comes in simultaneously all the possibilities are being applied here.
Yeah. So one point I want to add here. So simultaneously, but in classical one, if these 4 bits are B1, B2, B3, B4, then they will have only one value at a time. 4 bits are there, namely B1, B2, B3, B4, and value of B1 is 1, B2 is 1, and B3 is 0, and B4 is 1. So these values are fixed. So these 4 bits can take only one assignment, that is 1101 at a time. But here in quantum computer, these 4 qubits are there, and they can represent all the possible values simultaneously and can operate also on them simultaneously. So are you able to understand this thing? That in classical, you can have only one possible assignment at a time. You cannot have this 4 bits are there. You cannot have 2 choices for assignment. You will have only one at one time instance. Is this not clear? Because this is very important point to understand.
Sir, one more doubt I have got.
Yeah.
We usually say that in classical computers it cannot generate data. Is it the same with quantum computers, or is that it can simulate the data by itself? This all possible combinations.
Please repeat your question.
So usually in normal classical computers, this input data, whatever you have given, is usually given by users. Is that not?
Yes.
It cannot simulate or it cannot create data. But when you take this quantum computer, this set of data, what you have given, is it again loaded or is it automatically generated using the superposition?
No. Actually, what happens is that initially we start with all zeros. Basically, we will have this kind of state. 4 zeros will be there. Then we apply some Hadamard gate that will create superposition.
Yeah. Okay. It can create. That's it. So first initial input you have to load it.
Yeah. Initial input will be all zeros. So we will like in classical also when we do some programming. So basically what we do is we assign zeros to all variables. Then we change them in between the program.
Okay.
So the logic is same here. So anyone please, because this is very important concept, and if you are able to appreciate then the concept, then only we will be able to appreciate the benefit of quantum computer.
Sir,
So
one,
anyone
sir,
other
actually,
than her? Yeah, yeah, please.
actually, in say in classical digital electronics, if we
Yes.
want to apply 4-bit input, say for
Yeah.
example decoder,
Yeah.
4 to 16 decoder, 4 bits at a particular time, only one combination we apply,
Yes.
and accordingly the output will come. How it happens here, sir, in quantum? So 4 bits means all the possibilities how they can exist at a time. That I am getting doubt, sir.
Yeah, yeah, that we will see in the practical session also. So here this superposition concept is very basic to the quantum mechanics, and what we can say that it is there. Like this qubit can be in 0 and 1 simultaneously, but what happens is when we measure it, it will turns out to be one of them, either 0 or 1. But in between, system will be in this kind of superpositions. So that we will see in practical session also, that how this happen on actual quantum computer of IBM today in last session.
Okay, sir. Thank you.
So time being, you understand that this it's happening and it happen in that way. So if the same computation I want to do on a normal computer, then what I have to do is I have to apply this f 16 times on different values. Then only I will be able to match the computation of quantum computer. So if I have 16 such computer, then I can do in one go. Are you understanding me?
Sir.
What I'm saying is that same thing if I want to do on normal computer, because normal computer does only one thing at a time. So if I want to compute for all of them, then what I have to do is I have to do the thing in loop with different input values. So 16 times I have to run this f, while one iteration of f is doing the thing here. So we will repeat this thing and again when it comes. So single qubit we have seen. So single qubit can be in linear position of 0 and 1. When in case of 2 qubits, the system will be linear combination of this all 4 2-bit states. So in case of 2 bits, there are 4 choices: 0, 0, 1, 0, and 1, 1. So if we are having a 2-qubit system, and if we created superposition, then it will be having this kind of state: 0, 0, 0, 1, 1, 0, and 1, 1. So what is here we are saying is, if we are having a 2-qubit system that is in superposition, then it can represent this all 4 amplitudes or 4 states simultaneously. That is 0, 0, 1, 0, and 0, 1, and 1, 1. So, and the condition is that this alpha 0, 0 is what? It is basically the probability alpha 0 is the amplitude of this 0, 0 state. So when we measure this 2-qubit state, what is the probability of getting 0, 0? That will be mod alpha 0, 0 square. And probability sum of all these alphas will be 1. So in case of this 2-qubit, it can represent this 4 2-bit amplitude simultaneously. So if we go for 3-qubit, then it can have all 3-bit amplitudes like 000 to 111. So if we have this kind of 30-qubit system, then this 30-qubit system, and if it is in superposition, then it can represent this many amplitude. That is almost order of 1 billion. So are understanding the quantum parallelism or the quantum superposition benefit? So if we have just only 30 qubits, then we can have these many amplitudes simultaneously with us. And if we apply some f on this 30 qubits in a quantum computer, then it will be operated on all these inputs, all these amplitudes. So this is the benefit we are getting here. So if we are having a classical computer, then what we are going to do is we will take one choice of these 30 bits and apply f. Again, we will have other choice of f, other choice of this 30 bits, then we will apply other. But in case of quantum and in superposition, we can do in one go. Basically apply quantum gates on this 30 qubits, we will be able to perform those computation. Suppose if we are having 500 qubits, then what will happen? It can represent more amplitudes than our estimate of number of atoms in the universe. So see the benefit here. It can represent these many states. And if we operate on these 500 qubits that we can do, then we are able to manage these many amplitudes simultaneously. So we can see how exponentially qubits are giving us speed up, or basically parallelism, we can say. State space is increasing exponentially with the number of increase in qubits. So if 2 qubits are there and it is 4, then 30, it is almost 1 billion, and 500 we cannot count even. So any doubt here?
No, sir.
Anyone? I think someone should have doubt. Okay, then move ahead. So basically, so we have seen this 1 qubit, and as earlier we told that 1 qubit can be represented like this: alpha times 0 plus beta times 1. So basically what we are saying here is that it is a linear combination of both 0 and 1. Linear combination of 0 and 1. And the condition is that this mod alpha square plus mod beta square is 1. Okay. So this is Bloch sphere representation of qubit. So what we are saying is that it is a unit sphere, and all the vectors on surface of this sphere represent a qubit, a valid qubit. So let's suppose this. So what I am saying is that this is a unit sphere, and on the surface of this sphere, every possible point is a quantum valid state for 1 qubit. Like someone noticed, someone mentioned in the previous slide that alpha and this alpha beta can be anything. These are complex number, so this can be anything. So on this surface, infinite number of choices of alpha betas are there, and that will be a valid state if mod alpha square plus mod beta square is 1. So how we can represent this kind of state on a Bloch sphere? So basically it's a vector. So basically what we are saying is that we want to represent this qubit state mathematically. So what we are doing is we are saying that this psi is a vector, and we are saying that it is a quantum state, and it's alpha beta we want to determine. So what will be alpha for this vector? So alpha will be basically cos theta by 2. So what is this theta here? So first understand what is this theta and phi. Theta is the angle, the state, like psi state is there. So the vector is, what is the angle this vector is making with plus z axis. This is plus z axis, and we are denoting as a 0. This plus zx point is 0, and this minus z we are saying as 1. And in between are linear combinations. So what we are saying is that what is theta here? Theta is the angle which this vector make with plus z axis. Here this is the theta. And what is the phi? Phi generally we call as a phase. And what is this? When we take the projection of this psi vector on xy plane. So this is xy plane. You can see here. This is the xy plane. And we are taking projection of this on xy plane. So here is this projection. Comes here. And this projection, what is the angle this projection make with this plus x axis? So this is the angle phi, and it is called phase. So what is this theta and phi? I am just repeating again so that you should remember. Theta is the angle which is made with plus x plus z axis. This is vector, and this is the plus z. So this is our theta. And what is phi? Phi is the take the projection on the xy plane, and then projected vector, compute the angle from plus x to this projected vector. So that is phi. So what we are saying is that we can write as this alpha 0 plus beta 1 can in terms of this cos theta by 2 0 plus e power I phi sin theta by 2 times 1. So this and these are equivalent. And here also we can see this cos theta by 2 is basically alpha, and this e I phi sin theta by 2 is basically beta. And if you square and add them, then it also turns out to be 1. So if we vary this value of theta and phi, then we will get different states. Okay. So can anyone repeat what is this theta and phi once for me or for everyone? What is theta and phi? Anyone, please?
Theta basically is the angle that the vector psi is going to make with the 0 qubit.
Yeah, plus z axis, you can say.
Plus z axis.
Yeah. Okay.
And when we project the same vector on the xy plane,
Yes.
That projected vector, what it makes, the angle that it makes with the positive x is your psi.
Perfect. Thank you. Please be with me to help me out. Yeah. So if I say this is our zero state, okay, plus z.
Always the zero state is positive z axis only.
Yes, yes. So what is the let's suppose this is plus z axis. So what will be theta and phi for this plus z, or basically 0? Who was with me earlier? I want her to volunteer for me.
So sorry, I did not hear your question. Sorry.
Yeah, what I'm saying is that this zero state is here. So in case of 0, what will be alpha and beta? Alpha will be 1.
In
And
0, your alpha would be 0 and beta would be 1.
No. We want 0 here. So alpha should be 1.
The angle that it makes you're talking about, sir.
No. First, you tell me about alpha and beta. What is the value of alpha and beta if you want to have 0 as a psi?
Will be the magnitude with which 0. So if I say alpha 1, alpha is 1
and beta is 0.
Beta would be 0 in that case.
Good. Now tell me what is the value of theta and phi?
Theta with itself is 0.
0. Perfect.
Beta, when it is projected down,
yeah,
in the xy plane, is going to be.
So it will come to x only.
So x positive x, how much value it is going to make the z value is
so
90.
It will be, so no, it will be 0 only.
0 only.
Yeah. So what we are saying is we are projecting it on xy plane. So it will come to maybe origin, or you can say x axis only. So angle will be 0.
Okay.
So phi will be also 0.
Okay. Sir.
So we put the values of theta and phi in this equation. Then what we will get? If we put theta is equal to 0, then it will be cos 0. That is basically 1. And if phi is 0 again, so if I phi is basically 1 and sine theta is 0, so what we will get? 0 state.
Sir.
So let's suppose I am saying about this minus z, that is 1. So what will be the value for minus z, basically for 1? What will be the value of theta and phi? So minus z will be somewhere down here. So what is the value of theta? Theta
180 degrees.
Yeah, perfect. So that is basically pi. Okay.
Yes, sir.
Pi by 2 is basically
0.
And what is the value of phi? Phi again will be 0. And sine pi by 2, that is sine 90. So sine 90 will be 1. So we will add 1. So for different value of theta and phi, we will have all possible states. But some of these states are useful for us. That is basically 0 and 1. Let's suppose if I am talking about this state, somewhere over plus x. So what will be theta and phi for it? I'm here at plus x axis. So what will be theta? Anyone, please?
Pi by 2, 90 degrees.
90,
perfect. And what is phi?
Phi will be 0.
0. So if you put the value of theta and phi, so if you put theta is equal to pi 90, then here it is cos 45.
1 by root 2.
1 by root 2 0 plus phi is 0. So e phi is 1. And here also sine theta by 2, that is sine 90 by 2. Again it is 1 by root 2.
1 by root 2.
So what we are getting here is 1 by root 2 times 0 plus 1 by root 2 times 1.
1.
And the condition of this coefficient of this 0 and 1 are basically 1 by root 2, 1 by root 2. So if we mod square them, then it will be 1 by root 2 square plus 1 by root 2 square, that is basically 1 by 2 plus 1 by 2, that is 1. Please mute yourself once you speak. So here at plus x-axis, it is basically 1 by root 2 0 plus 1 by root 2 1. If you go for minus x, then it will be, anyone can please tell what will be at minus x-axis? So again, theta will be, anyone please?
Same 5 by 2, sir.
5 by 2.
Theta again pi by 2. And what is phi?
Phi will be pi.
Yes. So if we put ei instead of phi 0, we will put phi is equal to pi. Then it will be basically minus 1. Ei phi will be cos pi plus iota sin pi, that is equal to cos pi is basically minus 1. So what we will have here? The same thing here, but with negative sign. Here we are having 1 by root 2 0 plus 1 by root 2 1. On the back side of this minus x-axis, the sign will change here. Is it correct?
Yes, sir.
So now we have understood that based on this theta and phi, we can get this alpha and beta. Basically, coefficient of 0 and 1 we can get. And to be valid state, it should be mod alpha square plus mod beta square should be 1, always 1. Okay. And whenever we apply some quantum gates on this qubit, so basically what we are doing is that this is our current state psi. If we are moving it from here to here, let's suppose, or somewhere else, that is basically a quantum gate operation. Let's suppose if we are having 0 here and we apply something that the state changes to plus x. So what is a quantum gate? Basically just it is changing the state from one position to other on the Bloch sphere. Here I have shown that if state is here at plus x-axis, then it is basically 1 by root 2 0 plus 1 by root 2 1. So basically both 0 and 1 are here. If we see at this north pole, then only 0 is there. No 1 is there. If we see here at the south pole, then it is only 1. But if we see on this equator at plus x, we are having both 0 and 1 simultaneously. So just to keep this point in mind, that whenever we are doing some quantum gate operation on a single qubit, we are just moving this state psi over this Bloch sphere from one place to other. So in case of single qubit gate, what we are saying is that the 0 and 1 are basically our basis states. And the states can be written like this, 1 0. So, and the single qubit can be represented as a column vector. I think so, yesterday someone had covered that we can write this single qubit as a column vectors, and for one qubit there will be having 2 rows, and for multiple it will increase. So we are talking about the single qubit scenario. So 0 can be represented like 1 0 and 1 can be represented by 0 1. So basically same thing. Basically these are alpha beta. Alpha is 1 and beta is 0. Here you can see in case of 0, alpha will be 1 and beta will be 0. So for 0, alpha is 1 and beta is 0. So similarly also for 1, it is 0 and 1. So whatever state general qubit we can get using this 0 and 1's linear combination. So what we are saying here is that we can write linear combination of both 0 and 1. So basically these two vectors and the linear combination will give a general qubit state. So instead of writing qubits in this form, alpha times 0 plus beta times 1, we prefer to write it in a column vector, and where we use only this coefficient alpha and beta, because we clearly know this alpha is coefficient of 0 state and beta is coefficient of 1 state. So what is the point here to remember is that a single qubit state can be represented using a 2 cross 1 column vector. So these two values are basically coefficients of 0 and 1. So single qubit can be represented as a 2 cross 1 column. Suppose we are having these two qubits like this. X is 1 qubit and Y is other qubit. So how we can write as a combined system? So if we have joint state of these two qubits, then basically it is tensor product of these two qubits. So whenever we want to combine more than 1 qubit, basically we just have to do tensor product of them. So what we are doing is just we are having this state and this state. So we are just doing the tensor product. So everybody understand tensor product? Anyone please explain? What is the tensor product? This symbol, this cross symbol. Okay, let me tell you. So what we are doing, if these two qubits we want to do tensor product, then what is happening here is that this first thing is multiplied to everything in the other, second thing is multiplied to everything in other. Or if so here we can see like, and if in case of matrix representation, so what basically we are doing is this alpha 0 is multiplied with entire right hand side matrix, and then alpha 1 is multiplied by entire right side matrix. So each element of this, if you think in terms of matrices, then one element is multiplied with entire right hand side matrix, and then again for other element. And here if you see, then simply that one element is multiplied with the other things on the right hand side of the tensor. So here what is happening in the tensor? We are just multiplying this alpha 0 0 to this entire state. So it will be basically alpha 0 times beta 0, or basically these two qubits will be 0 0, and if you multiply them, these four states will be there. And tensor of 0 0 is basically a state 0 0, and tensor of 0 1 is 0 1, and tensor of 1 0 is 1 0, and last is this. So here what we are saying is that if we are having two qubit system and their joint state can be represented like this, tensor of this, and basically what we are saying here is that is this 0 0 can be written like 0 0 state, and this alpha 0 beta 0, if we called a new variable that is alpha 0 0, then we can write this combined state of these two qubits like this: alpha 0 0 times 0 0 plus alpha 0 1, and so on. So what is happening here is, in the two qubit system, we are having all possible 2-bit states, namely 0 0, 0 1, 1 0, and 1 1. And the condition remains same. These coefficients are the amplitude of these states, and this mod of alpha 0 0 square is basically probability of getting 0 0 on measurement. So if we represent the qubits in terms of matrices, then simply this tensor product of these matrices will give this thing, and we are just renaming these values. Alpha 0, beta 0, we are saying that it is, let's suppose it is alpha 0 0. So we can represent a 2-qubit state by a vector of 4 cross 1 matrix. So in case of 1 qubit, it was 2 cross 1. In case of 2 qubits, it will be 4 cross 1. So just to recap, so in case of 1 qubit, there were 2 basis states, that is 0 and 1. So in case of 2-qubit system, there will be 4 basis states. That will be 0 0, 0 1, 1 0, and 1 1. And any arbitrary state will be linear combination of these 4 basis states. So here we can see, and there some mode will be 1. So there are a few questions to you. If I'm representing this state, 2-qubit state like this, and the values of alpha zeros, alpha i's are like this, 0.316, 0.447. So when this state will be a valid 2-qubit state? Anyone please? Anyone please volunteer? My question is whether this state is a valid 2-qubit superposition state or not.
No. Sum of that should be 1. The amplitude square of sum, yes.
Yes.
Yeah.
So let's suppose it is a 1. Then it is valid state?
Yes.
And if I ask you what is the probability of getting 0 0 on measurement?
0.316
square.
Okay. Yeah, sorry.
Mod square. Okay. Then the next question is, what is the probability to read the rightmost bit as 0? This 2-qubit system is there, na? So what I'm saying is that right bit I want to read as 0. So what is the probability?
Mod of 0.316 square plus mod of 0.548 square.
Correct. So, thank you. Yeah. So this is the thing. So whenever these two states will come, probability sum of this 0, 0 and 1, 0. And what is the probability of getting 1, 1? Probability of getting 1, 1?
0.632 square.
Yes, perfect. So if we are having this 2-qubit system, I have shown that this kind of scenario will be there. If we are having n qubits in superposition, then this kind of scenario will be there. So there will be 2 to power n states, and they will be superposition state. So here, what is this 0 is basically n times 0. Basically, it is we are writing it in decimal, but basically it is, if you see in binary terms, then it is n times 0, and the last, this 2n minus 1 is the basically decimal equivalent of n times 1. So if we are having a superposition this n qubit set, then there will be 2 to power n amplitudes simultaneously, and their probability, we are saying it alpha zeros or alpha is basically the probability amplitudes. There is amplitudes, and the condition remain the same, that mod sum of this mod square will be 1. So there are some issues when we have this qubits in the actual physical implementation. So as we have seen in this Bloch sphere, there will be some theta and phi. Okay, so there are two disturbances caused by the environment, because these qubits work on the 0 degree Kelvin. That is basically minus 273 degree. At this temperature they work, because the quantum phenomena can be observed at that absolute 0 temperature. So if there is some interaction with the environment happens, then this qubit are disturbed, and in disturbance they lose their theta and phi. So basically, if we want to have a state in some particular theta is equal to 0 degree or phi is equal to 45, then this qubit cannot remain in the same state for longer duration. Maybe in milliseconds, it changes its states due to the energy relaxation or dephasing. So in energy relaxation, what happens is that let's suppose if 0 is our ground state and 1 is excited state. Let's suppose we are having a state in one state. Then due to this energy relaxation, the qubit can tends to 0. So 1 will change to 0 due to this theta changes. And whenever we are having superposition with this phi, so if in that case, what happens is, if you see here the Bloch sphere, that will be more clear. So what we are saying is that qubit can go from this one state to 0 when it loses energy, and this phi also disturb. If this phi disturb, then superposition we will lose. So it is basically the due to the interaction and the energy losses, there are implementation issues. So whatever operation we want to perform on these qubits, we are having limitation that we should perform this operation in milliseconds or nanoseconds only. After that, they will lose their original state or intended state. And this T2 is more important because dephasing time, because it will remove this superposition states. If this phase goes 0, then superposition will destroy. Whatever we want, it will not be in that state. So till now we have understood about quantum bits, and this quantum bits can be represented using Bloch sphere, and how a state can be represented on a Bloch sphere we have seen, and what are the challenges in implementation of these qubits. That is that they are having this dephasing time and this energy relaxation. Due to that, they lose their original state or the intended state. Now it comes to the quantum gates. So firstly, we will go through the quantum gates of which apply on the single qubit. Then we will go for multi-qubit gates. So there are two kinds of gate: single qubit gate and multiple qubit gates. In single qubit, we are having this poly X, poly Y, poly Z, Hadamard, phase gates, and in the multiple qubits, we are having various important gates that we will see in detail in following slides. Yeah. So in case of this, so what happens is that psi is given to us, and I have explained earlier that once we apply some gate on this psi state, it will change to psi dash. So when we apply this one quantum gate on a single qubit state, so basically what is happening is psi is on Bloch sphere. If I apply u on it, it will change its state on the Bloch sphere. It will go somewhere else. And this u is basically a single qubit gate. It can be anything, a single qubit gate that we will see. And what is the property of this quantum gates? These gates are reversible. In case of this classical scenario, the gates other than this NOT gate, all other gates were non-reversible. But in case of quantum, every gate is reversible. And if we if we convert this U gate to its matrix, basically qubits we can represent it as a column vector, and this quantum gates we can represent using a square matrix. For a single qubit, it will consist of 2 cross 2 matrix. Okay, and what we are saying is that all gates are reversible. So then, if we are having this U gate matrix, and reversibility is two matrix, one matrix is reversible if one matrix U is reversible. When it happens, when U dagger U is equal to identity. Now, what is U dagger? Basically, complex conjugate of this U. So this is when the matrix is U is reversible. This is the property. So when we represent this quantum gate using some unitary matrix, then the property of unitary matrix says that U dagger and the U dagger U should be equal to identity. So we will see in the all gates, quantum gate follow this property, and all gates are reversible. So first gate is this X gate. So what happens in that X gate is, let's suppose we are given qubits as C0 times 0 plus C1 times 1. So what will this X gate will do is, it will just swap the coefficient of 0 and 1. So basically, one state was having C1, so it will come C1 comes here and C2 goes here. So basically, if we see for basis states, it changes 0 to 1 and 1 to 0. So as we have already seen that 0 can be represented as a column vector like this, and the equivalent matrix for this NOT gate, that is basically 0 1 1 0. So what we are saying is, if we apply this matrix on a basis state, then it will behave as a NOT gate. So what we are saying is that if we apply this NOT gate 2 times, then we will get identity. So basically, this identity matrix represents that nothing is changed on the qubit. Like that, if we apply this identity matrix on some vector, column vector, then the vector will remain same. So what we are saying is that if we apply 2 times this X, then we will get the identity. So for a general state, if we see, then if we general state is like this and we apply X, then it will be swapping the coefficient. And if you see this X gate, what is this X gate is basically, it is rotation about X axis by pi degree, pi radian. So X gate is basically rotation about X axis by pi degree. So if you see the Bloch sphere here, so what we are saying is that, what is the X gate? Whatever the state is there, we have to rotate it around X axis by pi radian. So what we have to do is, to rotate around X axis, we have to take its projection on YZ plane. Then we will rotate around X, and then we will reflect back the vector. So it will go to somewhere else. Okay. So similarly, Y and Z get also. Yeah. So what I told is that just we are rotating the vector around X axis by 180 degree on the Bloch sphere, if you see. So basically, this is the matrix representation, and if you apply, then you can get this kind of results. Next comes this phase shift gates. So what does this gate does is, so as we have seen that state is having our general state has e to power I5 phase. So what this gate does is, it adds the phase phi to the state. So for 0 will remain same, but for one state it will add the phase phi. Okay, and this particular value of pi, if phase is equal to pi, then it will change the state from 1 to -1. So what is we are doing here is that let's suppose put the value pi, then e power I pi is basically minus 1. So for phi is equal to pi, it is just changing the sign of one state from 1 to minus 1. For 0, it will remain same. So this is our general gate where theta is the rotation, and this phase gate is basically nothing. It is basically rotation around z axis by theta degree. If we put theta is equal to pi by 2, then we call it as a S gate. Basically, pi by 2 rotation around z axis. So to rotate around z axis, what we have to do is we have to take the projection on xy plane and then rotate and then reflect back the vector. And T gate is particularly this pi by 4 value. And as I already told, if this theta is pi, then it is Z gate basically. Next comes is the important gate, that is Hadamard gate. So what does this gate Hadamard does? If we are having a 0 state, if you apply on 0 state, then it will convert it to 0 plus 1 by root 2. So what is happening here is this Hadamard gate can convert that 0 to linear combination of 0 and 1. And what is happening here is, if we measure this state, then we can get either 0 or 1 with 50% probability. Padam Charan Sahu, please mute yourself. And if we apply it on one state, then it will goes to 0 minus 1 by root 2. So we can represent this gate as a matrix of this kind. And what is the property of this matrix? This matrix should be reversible. So if we take complex conjugate of this matrix and multiply it with, then we will have identity. So we can see here, this is our H matrix, and we will take complex conjugate of it. So basically, complex conjugate of this matrix is the same matrix. So if you apply 2 times, then you will get identity. So every gate is having this property, reversible property. So reversible is basically if we take complex conjugate and multiply with the original matrix, then it will get identity. So basically here what we are having is 2 times we apply H, then we are getting identity. So it is self-inverse also. So what is this Hadamard gate is basically, if we see in the Bloch sphere, and if we are having this state 0 plus 1 by root 2, basically plus x we are having, and if we apply Hadamard on this state, then what will happen? It will basically does these 2 things: rotate around y-axis by 90 degree, followed by a rotation around x-axis by 180 degree. So see here, what we are doing is rotating around y-axis by 90 degree. So this will go here. So it comes here. And then we are rotating around x-axis by 180 degree. So this is our x-axis and rotated at 180. So it will come here. So it will come here. So what we are saying is that Hadamard gate is nothing but just a 2 rotation. One is y around 90 degree and x around 180 degree. So this is also reversible also. If we do in that direction also, we will get this thing. So if we apply it on 0, we will get this kind of state. If we apply on this state, then we will get 0. Next comes is multiple qubit gates. So till now we have seen this single qubit gates and all were reversible. Now comes is control node gate. So as the name suggests, whenever this this wire represent qubits, this B is a qubit, A is a qubit, and what we are saying here is that whenever this control qubit denoted by solid dot, it is 1, then change the sign, change it like this. So what is happening here is, if you see here, if control qubit is 0, then the target qubit will be same. A will remain same. If control qubit is 1, then it is going to change, or basically NOT gate. So what is happening here? We are getting NOT of A. So understood, I think here. And since it is a 2 qubit gate, so matrix of it will be 4 cross 4. And this matrix, if we apply on a 2 qubit vector, that will be 4 plus 1, then we will get the desired state. So see here, so this first qubit is the control and second qubit is the target. So we can see here, if we apply C0 on 0, 0, so as control is 0, nothing will happen on the target, so it will remain same. If we see here, this first qubit, that is 1. If control qubit is 1, then what will happen on the target qubit? It will change. Yeah, anyone can please volunteer here? So what we are doing is, if we are having this kind of state 0 0 plus 1 1, when we apply C naught over it, then we will get this, because first qubit is the control, so no change will on target. First qubit is control, it is 1, so second qubit will change. So here first qubit is 1, so it is changed to 0, from 1 to 0. And we apply agar C naught again, then we are getting the original state. So basically what we can say, that C naught is self-inverse. And that is truth table representation of this gate. So where, as I already told, that these quantum gates are reversible. So to be reversible, there should be same number of input and same number of output qubits. So this wire represents the qubits. So 3 qubits are there input and 3 qubits will be output. Here what we are showing is a Toffoli gate. What that is basically control NOT gate. So this A and B are control qubits and C is target. So what will happen in this gate? Whenever this A and B are 1, then only C will change. Otherwise, it will remain same. So it will make effect on this last two vectors. If you see here, this A and B both are 1 here. So target is 0. So it will change. So it is changed here. When A and B are 1, target is 0. So it will change. So what is happening is, whenever this control are 1, then only it will make effect on, and this plus denoting here simply a NOT gate. So it will change. If we represent this as a matrix, then for 3 qubit, the matrix size will be 2 power 3 cross 2 power 3. Okay, that is basically 8 cross 8. So, and I am showing here that it is self-inverse. Basically, if you apply 2 times this gate, then we will get the original state ABC. So, a question to you guys: can we use this Toffoli as an AND gate? Anyone, please? Can we use this Toffoli as an AND gate? Yes, we can use. If we put C is equal to 0, then it will basically give AND gate. So if we put C is equal to 0, then it will be perform as an AND gate. And if we put value B and C, B is equal to 0, C is equal to 1, then we can use it as a NOT gate. So basically what we are saying here is that using this Toffoli, the single gate, it will work as a universal gate to implement all classical gates. Because we are having this AND and NOT here. So using AND and NOT, we can get all kind of gates. Basically, NAND gate also we can implement. So using this Toffoli, we can implement all classical logics. But to have a Toffoli gate of 3 qubits, we should use the basic gates, and then we can have this kind of derived gate. So to have this kind of this thing, we have to, if we want to construct Toffoli gate, then we should use this number of gates. There are almost 14-15 gates, basic gates, to implement one Toffoli gate. And if some errors are in this, then this error will also accumulate. So there are physical engineering challenges to implement a Toffoli gate with perfection, because it consists of so many gates, and these gates are having some errors. So that error accumulates, and designing perfect gate is engineering challenge. What is the swap gate? It just swaps the 2 qubits. So if we implement this 3 C0 gate in this fashion, then this A and B will be swapped. I think we are running out of time, so I will quickly finish the slides. So we can see the derivation here also, that if we implement this C0 in this fashion, then we will get swap this A and B. It is required most of the time. So this was the swap gate, and if we have a control swap, then there will be a control qubit will be there, and if the control qubit is 1, then this swap will perform. So if we can get this kind of gates also, control swap, and the matrix corresponding to that gate is this one, and control swap is called as a Fredkin gate. So sometimes like this single qubit gate is represented by 2 cross 2 matrix, and if we are having this kind of control U gate, then what will happen is basically it will have two inputs, and one is this when this control solid dot is 1, this qubit is 1, then only it will perform on target qubit. And sometimes we are having two control to perform this U operation. So if we are having let's suppose if you want to perform this kind of gates where 5 qubits C1 to C5 I want to make as a control qubit, then we can implement this C5 control 5 qubits as a control and apply this target qubit U operation. So if we use this triples in this fashion, then we can implement for n is equal to 5, we can perform this control U operation. This thing I will cover in the practice session also, that how we can do this kind of thing. So no need to worry about this. So one important thing I want to explain you to keep in mind that this wire represent the qubits. This Q0 and Q1 are qubits, and U and V are single qubit gates. So if we want to see this as a whole system, then we should have tensor product of this Q0 and Q1, and also U and V we can have tensor product. So earlier these were single qubit gates, and U cross will be a 2 qubit gate, and its matrix size will be basically 4 cross 4. So when we tensor this 2 cross 2 matrices, then we will get a 4 cross 4. Here also, if we are having this single qubit system, and it will be represented by 2 cross 1 matrix, when we tensor them, we will have 4 plus 1 vector. So here just I am saying that if we have two gates UV in this fashion, and equivalent of that will be tensor of them, and that will be a 4 plus 4 matrix. So as in classical scenario, this quantum also has universal set of quantum gates. But in case of this classical, they don't have this kind of gate, Hadamard, phase, and these gates they don't have. So for them we have this Toffoli gate. Using Toffoli we can implement all classical gates. But for universal quantum gate set, we should have this kind of phase and Hadamard with us. So if we have these 4 gates with us, then using them we can represent all the quantum gates. As I have earlier explained that using this C0, Hadamard, and this T gate, we can construct Toffoli, and using Toffoli we can implement all classical gates. So I am over now. If participants have any query, then they can ask me. Or I think in the practical session in the end, we will covering the same thing with examples on a quantum simulator and quantum computer. Any questions?
Excuse me, sir.
Yeah, please.
Sir, the transformation matrix that you are writing, sir,
Yes.
is there any particular way for writing it, or like?
Yes, yes. Just a second.
Yeah, sir. For Toffoli also, like.
Yeah.
You have
So
taken
see
8
here.
cross 8. Yeah.
Yeah. So see here. These are the inputs. ABC are the inputs, and these are the outputs. So as I told that every gate should be reversible. So same number of input and same number of output. Okay. This thing is clear. And what it does is basically whenever both the input A and B are 1, then only it will change C. So if we see in this truth table for the input conditions, first 6 value there is no this A and B are not 1. Only on the 7th and the 8th entry we can see A and B are both 1. See here?
Yes, sir. Yes, sir.
So then only what is happening on the C will be complemented. Okay. So if we see that this first 6 matrices, first 6 entries, it is going to be identity. Whatever the input is there, it should be the output. Okay. So what is happening here is that this AB, this 110 is going to the 8th entry. This 111 is going to 7th entry in the output. Just swapping of this 2 input state. If you see here closely, first 6 remain same, 7th and 8 are swapped. Okay, are you seeing it?
Yes, sir. Yes, sir. I can see that.
So what will happen in that case? As I told that for 3 qubits, the gate size will be 2 power 3 cross 2 power 3. Okay.
Okay.
So what will happen is first 6 entry we don't want to do anything. So that will be treated like as an identity matrix. See here till here.
Okay. Okay. Okay, sir.
Last this, if you see this sub matrix here, 0 1 1 0. That is basically the NOT gate matrix. What it does is changes 0 to 1 and 1 to 0. So
Okay,
what
sir.
we want to do is, here will be the 7th state and 8th state. So first 6 will remain same, 7th and 8th will be swapped using this logic here.
Okay, sir.
So what will be our input state? Our state will be like this. So 3 qubit state will be represented by 8 cross 1 column. Are you getting it?
Yes, sir. Yes, sir. So if it was two input, then it would have been 4 cross 4, right, sir?
Yes.
That is a pattern. Okay.
Yeah. So here is the logic only. So otherwise it is identical. Are you getting it?
Yes, sir. Yes, sir. I got it. Thank you, sir.
Okay. Any other question, please? Dr. Panda, and there is no more question?
Yes, sir.
Yeah.
Thank you, sir. Thank you for the valuable information. Again, we'll meet 12 p.m., sir.
Okay.
Participants, those who have not filled the attendance form, kindly fill it. And again, we will start the session at 12 p.m.
Okay. Thank you.
Thank you, sir.
Okay.
Thank you so much. Participants, again, we'll meet at 12 p.m. Now I am going to end the meeting. Thank you all.